4, 3.
Buenas tardes a todos. Daremos en pocos segundos inicio a la sesión número 7 de el ciclo de conferencias del profesor Molnar. Hoy nos va a estar hablando acerca de New Zealand y el sur de los Alpes. Peter.
Thank you. Okay. Thank you, Hector. So yes, today I will be talking about New Zealand, the Southern Alps, as a very good example of how we can study vertically averaged lithospheric strain and low temperature conditions and low temperature constitutive relations. And this is a view looking from the west, from offshore on a ship towards the Southern Alps and high peaks. I think this is Mount Cook, the highest peak, but I've forgotten, I may be wrong. And then you see the ocean here down at the bottom. So New Zealand is a small emergent part of a bigger piece of continent. So the gray outlines the North Island of New Zealand, down here the South Island of New Zealand, and then some smaller islands here, down here, up in here. But the orange and red and green are regions of shallow ocean floor. It's only the blue and the purple that are deep. So oceanic crust underlies all of this deeper blue, but this is continental crust. It's just thin continental crust and hence below sea level. So New Zealand is continental, but one sees only a bit of it because of only a bit being above sea level. And the main sense of motion, and I'll show this in more detail, is strike slip, where the region to the northwest moves northeast relative to the Pacific plate to the south. And you have high mountains. You have a big fault, a major fault going along here, the Alpine Fault. I'll say more about that. In the north, it spreads out, splays into a series of faults. These valleys are all following along strike slip faults. And there's high terrain because there is some crustal shortening, not very fast, not very much. And then there's a bit of old volcanism. This is actually an old volcano. You can see the surroundings with the remnants of a caldera in the middle down in here. Why New Zealand? Well, first of all, we know the relative plate motion well, and I'll show you this. It's mostly strike slip, which makes it easier to study than where there's convergence. We know the total offset since New Zealand began to deform, 850 kilometers. I'll show you wave splitting, seismic anisotropy, shear wave splitting, and both also PN travel times. These are clear and large. You may disagree about whether PN is so clear, but there's large measures of anisotropy, and this seismic anisotropy allows a test of how strain occurs in the mantle, and therefore its rheology, the rheology of the mantle. So New Zealand illustrates well continuous deformation in the mantle lithosphere, not slip on through-going strike slip faults. So I'm going to show you now an animation made by Steve Candy. This goes backward in time. So today is 0 and it will go back to 80 million years. This is New Zealand up in here. The plate boundary is oversimplified. It's shown there'll be a subduction zone up here, but then the plate boundary goes through New Zealand approximately along the Alpine Fault. One has spreading today between Australia up here and Antarctica, and between the southeastern part of New Zealand and Antarctica along the East Pacific Rise. But earlier, this part of New Zealand broke away from Australia about a spreading center in here. So if we run this backwards, going back in time now 10 million years ago, you see New Zealand unslipping. So there's big strike slip, but earlier it was a different form of deformation. And then you get back to 40 or 50 million years ago and there's no deformation of New Zealand at that time. I'll run this just one more time so that you see this. Again, see New Zealand is undoing the strike slip faulting. It's right lateral, but this now shown as left. Back at 40 million years ago or so, 45, since that time, all of the deformation, nothing before then, and then you go back and close everything up. It's imperfect. You have some overlap back up in here. If one looks at a geologic map, a simple geologic map, I want to point out a couple of important regions. This in here, this is called Dunn Mountain. Dunn Mountain. This blue down in here is called the Mai Tai terrain. Dun Mountain is the place where the rock dunite was first found. This is a piece of mantle. So this is an ophiolite suite with mantle rock in here. Dunite is an olivine-rich piece of the mantle. And one sees it continuing down here. And then there's the alpine fault, the strike-slip fault that goes through here. So one has two ingredients, strike-slip faulting along here, but also, obviously, this region has been bent severely, and the adjacent rock has also been bent severely, and I will argue that this northern part has also been bent. So there's been strain. If one reconstructs where the North Island lay relative to the South Island not moved, at 45 million years ago, this is from Rupert Sutherland's work, the North Island would be down here. The Dun Mountain region would lie down here 850 kilometers from its present position. But also you see that the North Island is oriented differently, and there is, through the North Island, a big magnetic anomaly. Follows this. This is due to buried iron-rich rock. Dun Mountain is iron-rich. It's iron magnesium silicate from the mantle. It's buried underneath here, but it produces a big magnetic anomaly. And the bend in this suggests that it once was straight. And if one takes the bend in the reconstructed position and projects it back, one gets a straight line through here. One unbends this part and one aligns these in this way. And I should say, there is paleomagnetic data from rock in here that shows declination anomalies, shows that this bending has taken place. And so to take away from this, there's 460 kilometers of strike slip on a fault, but there's 850 kilometers of displacement. So some of that is due to just shear in the rock as exposed on the surface. If we just look at the last 20 million years, this is where a piece on the Australian plate lay relative to the Pacific plate at 20 million years ago. So this point is moving here to 10 million years ago, here to 5 million years ago, and moves to that point. Another point, 20 million years ago, would move here to 10 here, and then the present position. And so you see that it's largely strike slip, but there is a convergent component. There is a small component of convergence between the Australian plate and the Pacific plate on the opposite side. And if one decomposes this into the parallel component, it's been pretty steady at 30 to 35 millimeters a year for the last 20 million years. But the convergent component, the component perpendicular to the Alpine fault, has accelerated. It was very slow back between 20 and 10 million years ago, and it's accumulated. So the mountains in here, the crustal shortening is quite young, only probably something like 10 million years old in here. Now today, I'm going to start by focusing on the strike slip part. If I run out of time, I have material on the convergent part, and I'll put that later in a later lecture, but maybe I can get through all of this. I'm hoping so. If one looks at the fault itself, here it is. That's the fault right there. Nice sharp line. Here are two people for scale. That person is standing. That person is sitting. And what you've got here is Quaternary gravel. These are all boulders. These are big pieces of rock. This is the size of a person's head. In Quaternary gravel, this is sheared metamorphic rock. This clearly has been thrust over the top of this Quaternary gravel. These are tree stumps that are slumping downhill. This is not in the rock. So the convergent component is undeniable. If one looks at the modern day GPS, this is plot velocities relative to the Pacific plate. So down in here, there's almost no movement relative to the Pacific plate. When one gets near the Alpine fault, the motion is quite rapid. If one makes a profile, 0 being 0 lying at the Alpine fault, and then numbers increasing to the southeast in this direction, the strike slip component decays away, but decays away with a rather large distance. It's not sharply defined at the Alpine fault. Some of this is elastic strain, but much of it is not elastic strain, I will argue. And the convergent component, again, one sees the convergent component, again, spread over quite a large distance. This black line is just a fit to a curve. I haven't shown you what that's from, but obviously it doesn't fit the data right in here. If we blow this up and now fitting it a little differently. What was done to fit it was to put a dipping fault under the alpine fault. The alpine fault is at 0. Another dipping fault down in here. This is merely a gimmick to try to fit these data. The data don't really, there's no fault down here. That's just an excuse to fit the data. The point is, in order to fit these data, one has to spread deformation over a wide area. So it's widespread, and this looks like continuous deformation. Of course, this is too short a period to be sure, because an earthquake could undo a lot of this. Now, I remind you, I'll show this again, the alpine fault is very sharply defined. You can see it in the topography. This is topography coming across. The green is low elevation. The blue, of course, is ocean itself. So the higher elevation, the higher mountains are in here. But it's a very sharply defined fault, no question about it. And so one question is, well, does this fault go all the way through the lithosphere? And so I'm going to assume no, and I'll come back to this topic later, but assume for now that the anisotropy that I'm going to discuss is in the lithosphere down in here, and I'm going to ask the question, how wide is the zone of anisotropy, and therefore the zone that's sheared, and what controls its width? Why is it spread over a wide area? And I remind you, from this cartoon, if you have strike-slip faulting and sufficient slip, the strain in a region underneath where the deformation is continuous, in that case, the P wave will propagate fastest along parallel to the strike-slip faults, and the S wave, the polarization of the S wave coming up, will be fastest polarized parallel to this. So imagine this is an S wave coming up through the mantle, through the mantle lithosphere, through the crust. It's split. The faster, the earlier arrival is polarized parallel to the strike-slip faults. The perpendicular lower S wave, quasi-S wave, is perpendicular to the faults. And remember that the anisotropy is aligned parallel to the maximum elongation, and this can be written in terms of the orientations of crystals in olivine, I should emphasize. But I won't say too much about that. This picture is one I want to leave you with, and I'm going to take you back to an older paper using older data. I'll show you newer data in a minute. But what this shows, the black lines are the measured orientations of shear wave splitting, and you'll notice that they're pretty nearly parallel to the alpine fault. This line, this black line across here, is not quite parallel to the alpine fault. It's parallel to relative plate motion. The alpine fault trends along here. And so these orientations are nearly parallel to plate motion. But as you go farther and farther away, the strain should be smaller, and the orientations of the shear wave splitting, the black lines, are shown here as with these orientations changing. The white boxes are predictions where what Moore, England, and Parsons did was say, we'll use the GPS measurements, and we'll assume the distribution of the GPS measurements integrated over time give us a strain field. And the point, of course, is that the orientation of the maximum elongation shown by the white boxes is quite closely aligned with the maximum orientation from the shear wave splitting. At most of these sites, not all of them, that's not such a good fit. That's a poor fit. In fact, that's a good fit. Pretty good fits in here, a poor fit in this case. So I want to leave you with that. The match of the orientations, not the magnitudes, the anisotropy, assuming an exponential southeastward decrease of strain. They've assumed it decreased away as the GPS suggests it does. Now, afterwards, I was part of a project where we put ocean bottom seismographs offshore, off both coasts. And what are shown here, these red lines then show the orientations of the polarizations of the faster quasi-S waves. And hence these would be parallel to the maximum elongation in the strained region. And the alpine fault is the black line underneath here. And you can see, once again, near the fault, you're nearly parallel to the fault, nearly parallel to relative plate motion. Relative plate motion is approximately that arrow. And as you go farther away, they deviate, in fact, become perpendicular over here, probably this is something that's frozen into ancient lithosphere, and they decay less rapidly as you go away in the other direction when you're going to the northwest. If one takes these and makes a profile, aligns them over a midpoint, this is not aligned on the Alpine Fault, actually, it's aligned a little bit off it. The biggest values, these red dots, these are very nearly parallel to relative plate motion. Relative plate motion is north 60 east, and these are deviations from that orientation. So near the center of this, one has orientations nearly parallel to the maximum elongation, and the maximum delay time splitting is also located in these values where the strain is allegedly maximum. So polarizations of fast quasi-S waves define orientations of maximum elongation. The lengths are proportional to split times, and those scale with the strain, total finite strain, and the thickness of the layer. Say that again in a minute in a different way. So I remind you, pure shear, where you flatten a region and you stretch it in the orthogonal direction, you wind up with this orientation, or simple shear. New Zealand is simple shear, where you take a circle and you shear it and make an ellipse, a strain ellipse that looks like this. And the maximum elongation is defining the orientation of the fastest propagation of P waves. I'll talk about that later. And the fastest orientation of the polarization for S waves. So S waves coming out of behind the screen towards you, the faster of the two quasi-S waves would be aligned parallel to maximum elongation with that orientation, or in this case, parallel to maximum elongation, as in this case. And one can use this as a strain gauge insofar as the strain isn't too large. If we imagine we start with a circle and we have a shear zone with width W, and we displace one side a distance D with respect to the other side, we stretch out into this red strain ellipse. And the relationship is simple. The tangent of 2 times this angle is simply the ratio of twice the width divided by the total displacement here. And the amount of strain in here, this epsilon 1,1, the maximum elongation, that's simply the cotangent of this angle. And you can see that as you get larger and larger, this angle becomes smaller. Cotangent, therefore, of course, becomes, the cotangent becomes bigger because it varies inversely with the angle. And this tangent of 2 theta, as you strain further and further, gets smaller. Well, that's because the distance becomes greater. So we can use the anisotropy to get at these because we know the displacement. We know we can reconstruct back how much displacement has occurred between the North Island and the South Island, 850 kilometers, plus or minus 100 kilometers. And we can guess some widths. Suppose it's 100 kilometers or 200 kilometers. Well, if we put those numbers into this formula, we predict that the angle will be 6.6 degrees relative to the orientation of maximum shear, or for 200 kilometers, 12.6 degrees. This orientation of maximum shear, of course, would be the orientation of relative plate motion. So this is 6.6 relative to the orientation of maximum of relative plate motion. So we take that 6.6, and the relative plate motion is north 60 to east. We would predict the strain for this particular case be oriented north 53.4, or if the width of the zone were 200 kilometers, we would predict 12.6, and therefore the orientation north 47.4 degrees. But I emphasize the orientation of the fast polarizations is closer to north 60 east. It's closer to that number there. So if we can look at this in another way. We've been looking at the orientations. We can look, remember, we get the splitting. The split time is the time difference between the 2 quasi-S waves. So if I stop this here, the quasi-S wave that's polarized parallel to the maximum shear, this one, will arrive earlier than the other quasi-arrival and the quasi-S wave, and the time between them will depend on the thickness of the layer through which they've propagated and the magnitude of the anisotropy. it's the two numbers are not in, or the split time isn't a direct measurement of either the magnitude of anisotropy or the thickness of the layer, but it depends on the two of them together. And if I go back and we look at the split times instead of the orientations, let's assume the anisotropy is confined to the mantle lithosphere, and we'll take numbers of roughly 100 kilometers or roughly 200 kilometers. And I've made these 92 and 184 because the mean S-wave speed is 4.6 kilometers per second, and this number is easily divided by that, so is that. So the average travel time would be 20 seconds or 40 seconds through a layer 184 kilometers thick. But the split times between the fast and the slow quasi-S waves, these range from 1.5 seconds to 2 seconds, even a little larger than 2. So 1.5 seconds is 7.5% of 20 seconds, or 3.75% of 40 seconds. In this case, 2 seconds is clearly 10% of that. These are very large amounts of anisotropy. This is not a small value. Now, Reby took those values and allowed them, made calculations where one can go from the fraction of anisotropy given here, where this would be 1%, 0.01 would be 1%, 3%, 5%, and calculated how much strain is needed to produce this much anisotropy. And that's what these curves show. Don't worry about this curve. These curves show this. Excuse me, Sarah, could you lift that and set it down? And plotted here is a measure of strain, but his term for strain is a little different from what we're used to. So I've converted this into the elongation, where this would be no strain down here, no anisotropy, no strain, and then as you increase the strain, you get increased anisotropy. Well, 6% anisotropy, taking a number in the middle of that range, is off his scale over here. 6% would imply this would be 6% up here. This is 5%. If we then project onto this curve, we get a value that's up here, and that calls for an elongation of 2, a strain of about 2 in here. Well, let's go back to this. If we put a strain in of 2 with a cotangent of theta, then we get an angle of theta equal 27 degrees in here. That's a rather large number. But if we say, well, we know the displacement, and we go back to this formula, and we put 850 kilometers in here and calculate what the width would be, assuming 27, we get a 600 kilometer width. The width of the shear zone, in fact, twice the width of the shear zone, would be twice 600 kilometers. In a picture like this, we're doing that. It's putting 27 degrees in here, assuming a displacement of 850 kilometers across the region, 600 kilometers. But that's ridiculous, because 600 kilometers is this kind of a dimension up in here. This is wrong. This is categorically wrong. So there's some assumption that we've made that's wrong. Surely not assumption of the displacement, because the plate reconstructions are good. So what have we done wrong? Well, if we say, no, actually, the alignment in here isn't 27 degrees. The alignment is less than 10 degrees. The orientation of the maximum of the polarization with the faster quasi-S wave, and hence the orientation of theta in here, of this ellipse, is much closer, less than 10 degrees. It's not 27 degrees. We throw out the 27. We reject the 600. We put in 10 degrees. We wind up with a width that's more like 150 kilometers. And 150 is not too bad. 155 kilometers is not too bad for the width of this zone. That's to say that the anisotropy is localized within 150, 155 kilometers, one side and the other side. Both are about the same. So what's this saying? Well, let's go back to laboratory measurements. This is the case of what's the orientation of the 100 plane peak to the shear direction. So the shear plane is oriented this way, and that's the 100 peak. That's our maximum elongation. That angle rotates around as you get shear, And this is strain, 100%, 200%. These are enormous strains. This is the curve that one gets by assuming finite strain and with simple shear. This is nowhere near 10 degrees. 10 degrees is here. That would call for an enormous strain, much larger than a factor of 2, much larger than 200%, what we were using before. So the simple explanation is there's dynamic recrystallization. What's happened is the olivine has deformed enough that it's aligned parallel to the plane of shear, parallel to the plate motion. So if we go back to this arithmetic, the split times are telling us we've got a huge amount of strain. The values of those split times are suggesting a wide strain zone, which is wrong, but the orientations are suggesting a much more localized region, and hence what we have is dynamic recrystallization. The olivine is becoming aligned with its maximum elongation parallel to relative plate motion. So I'm going to turn to P waves in a second, but just to remind you, the axes of fast quasi-S waves and shear wave splitting are parallel to the orientation of maximum elongation. But if dynamic recrystallization occurs, the fast orientation becomes parallel to the shear zone. Okay, well, let's ask a different question. Maybe all of what I've told you is wrong, and the anisotropy is not in the mantle lithosphere, but actually lies in the asthenosphere lies down here. The anisotropy is down here, and this will explain both the orientations and the wide distribution. This is a possibility. To get at this, we're going to use P waves, but asking this question in a different way, could the alpine fault pass through the entire lithosphere as a fault? So this alpine fault dips under the mountain range, but it doesn't just spread out in a shear zone in the crust, but is a fault going all the way through the mantle lithosphere. And hence the anisotropy would be in the asthenosphere below. There are plenty of places in the world where seismic anisotropy is in the asthenosphere. This is a quite reasonable possibility. But to do this, we're going to look at P waves, because the direction of P waves, the fast propagation direction of P waves, is parallel to the maximum elongation also. And the P waves propagate in the uppermost mantle. So we can ask the question, do P waves show anisotropy? And does PN anisotropy beneath New Zealand indicate dynamic recrystallization? Again. So first, going back to some work, I'll show you more of this later when I discuss crustal shortening. But many years ago, back in the 90s, 2 refraction profiles were shot across the island, line 1 up here and line 2, but also a line was shot offshore, line 3W off in this area. And when Sherwoth et al. Measured the PN speed along line 3W, almost parallel to plate motion, the speed was very high, 8.6 kilometers per second. This is extremely high. You cannot get this in olivine without anisotropy. When they looked perpendicular, they got a very low speed, 7.7 kilometers per second. So this screams anisotropy. This requires anisotropy. And going back to Reeby's work, now looking at P wave anisotropy. So this is the fraction of anisotropy, and I remind you, 8.6 with one orientation, 7.6, take the difference being 0.9 divided by 0.81. This is 11% anisotropy. So again, one of Reeby's plots, 2%, 6%, 10%, 11% would lie up here. If you project on his curves, you would predict a finite strain up in here of about 2, an elongation of 2. The same as we got for shear waves, but of course, this gives you the wrong orientation if one goes to the formulae. So let's look at this in another way. Again, using this network of ocean bottom seismographs offshore and stations on land, looking at PN anisotropy. Again, PN, the P wave that propagates in the uppermost mantle just below the crust. First thing you notice, so what do we have here? These are apparent speeds between pairs of stations that are at least 100 kilometers apart. and their back azimuths are within 3 degrees. So these are measurements of a speeds where the path is between the two stations, very nearly between the two stations. And because they're 100 kilometers apart, the average speed is the speed in the mantle. The crust has been taken out of this. And what's plotted then is back azimuth orientation here. So 0 would be north, 180 would be south, 360 would be north again. And first thing you see is an enormous scatter. And this is work that I was involved in, and we don't understand the scatter. And this has been a huge frustration, but we have to live with it. What is shown in the black are binned averages. So the average within 15 degrees of this azimuth is binned into this. You can see large errors, but you can see a pattern that looks anisotropic, with the faster orientations aligned near plate motion, north 60 east. The slower orientations perpendicular to that. Perpendicular north 60 east would be north 140. North 140 east would be the slow orientation. The magenta line is showing you what you would have fitting the data, and the red line is showing if you're aligned with north 60 east, as I recall. So you can see a hint of anisotropy taking all of the data. And I should point out, north 56 plus or minus 3 is very close to north 60 east. So the data on average, ignoring all the scatter, suggests anisotropy parallel to plate motion. Now, if we consider smaller regions, we consider only stations, for instance, in this dark red box in here. So we ignore all data to the stations out here and all the data to stations way out in this direction, we get this plot. And you can see again, the binned data suggests quite marked anisotropy. Be nice if we had more data. Again, the orientation is very close to north 60 east, and the magnitude of anisotropy is large, 8%. This is not a small number. Then north 59 plus or minus 3 is north 60. If you include a bit more to the southeast, this dashed line, you get a different orientation and a smaller magnitude of anisotropy, and that's partly because these are even different. If we include this 12C box that includes this station in addition and excludes a couple of stations on this side, actually you wind up with an orientation north 60 east with a magnitude of anisotropy of 8 plus or minus 1%. This is quite fast, and again, the anisotropy is parallel to plate motion. If one just considers blocks out in here, starting with the biggest block, the blue one that includes all of these data, it looks like you see a hint of anisotropy, but it's not very large. It's still oriented not far from north 60 east. If you exclude this and you look only at the region that goes out this far in this dashed line, this 14E, that's this one down here. It's bigger, but it's still not 8% because it's excluded too many of the data that are in close, and it's included too many data that are farther away in here. If one plots the magnitude of the anisotropy, again, a couple of cases of 8%, and plots these as a function of distance from the alpine fault. So this would be on the northwest side, this would be on the southeast side, and the boxes, this is the width of the box used to get this average value. This is the scatter in the data. You see a peak near, but a little bit west of the alpine fault, with rapid decay in times going away from the alpine fault. If you look at the orientations on near the alpine fault and to its west are nearly north 60 east, parallel to plate motion. It decays away on the southeast side. This is probably anisotropy frozen into the Pacific plate on the New Zealand crust. So if we go back and do the same arithmetic that we did before, go back and remind ourselves, this is what we did with S waves. We found with S waves, and we put numbers like this in. If we say we've got widths of shear zones that are 100 or 200 kilometers, we predict orientations of this kind. The S-wave polarization would be predicted to be maximum with this angle, or this for a 200-kilometer wide zone. But we measured S-wave polarizations close to north 60 east. Well, if we look at P waves, same numbers, P wave fast propagation, but again, the fast P wave propagation that we observe is close to north 60 east, close to plate motion orientation. And so there are two conclusions that we draw from this. First, because PN propagates just below the MOHO, here's the crust, here's the mantle lithosphere, not way down in the asthenosphere, this arrangement is wrong. The fall not penetrate all the way through the mantle lithosphere into the asthenosphere. The anisotropy cannot be in the asthenosphere. The anisotropy must be in the lithosphere. And the PN, and the S-wave splitting agree on a width that's of order of 100 kilometers or so. The width of the shear zone is of order 100 kilometers, although, of course, it's not just a finite number. It's not just one number. It decays, as I will argue, exponentially. So shear wave splitting with orientations of polarizations of the fast quasi-S waves aligned parallel to relative plate motion, and PN propagation with fastest propagation aligned parallel to plate motion. Both of these are pointing towards dynamic recrystallization because you'd have a different orientation if you didn't have that alignment. So let's go back to what we had last week. Widths of shear zones that where strain obeys a nonlinear viscosity of this kind, strain rate varying as shear stress to a power n, n for mantle material would be of the order of 3, and the strain rate decays exponentially with some constant x0. This is the exponential e-folding distance, and that depends on the length of the boundary divided by 2 pi and the square root of n. Again, we're putting in n equals approximately 3 into this. And for the length of the boundary is at least the length of the alpine fault, at least 500 kilometers, and could be 1,000 kilometers, taking that, the zone, the entire width of this zone in here be more than 850, something like 1,000 kilometers. If we take those numbers, n equals 3, let the length be 500 to 1,000 kilometers, we predict this e-folding distance to be approximately 50 to 100 kilometers. And that's essentially what we're observing. This distance, this fall off, is rapid over a distance of 50 to 100 kilometers. And the orientations, they don't change on this side, but they fall off rapidly with that same kind of a distance. And so we conclude that deformation of lithosphere beneath New Zealand, deformation, continuous deformation, not faulting, passes this test that's been imposed on it by the anisotropy and the relationship of anisotropy to strain, to finite strain. Now, we can just think about temperatures. The heat flux beneath New Zealand is rather typical, 60 milliwatts per square meter. So the temperature at the MOHO is probably of the order of 600 degrees C. And in fact, for a MOHO, that's a MOHO at 40 kilometers. If for a MOHO at 40 kilometers, it's probably even a little less, 500 degrees C. And if we think about a gradient of temperature of 10 degrees C in the mantle underneath a typical value, we would predict that the temperature of the MOHO 15 kilometers below the MOHO in the mantle would be of the order of 650 kilometers. And if we look offshore, where the crust is thinner, then 15 kilometers below a thinner MOHO, predict a temperature that would be even a little colder, 550 degrees C. The point here is that these temperatures are in the range where Peierls creep is what's important. I've used, as you've noticed, the dislocation creep for some of this, but Peierls creep will be operating at the very shallowest depths. And that requires dynamic recrystallization at a very low temperature. This is a result that many people won't care about, but this is a surprise. And I think most people don't believe it. And yet I don't see how one can escape it. This is a very low temperature for recrystallization to be occurring. So now I want to turn to the other side of this, the convergent part. And remember, I showed you there were lines of seismographs that were installed across two lines, line 1, line 2, and refraction profiles were shot across the South Island in here. Well, we also recorded distant earthquakes from Honshu, from Irian Jaya, from the Banda Sea, and another one coming from Chile on the other side. This one wasn't recorded that well, not particularly well. I might point out that all of these earthquakes, these are intermediate and deep earthquakes in the Pacific Plate under thrust beneath New Zealand. And these are mostly intermediate depth earthquakes in the Australian Plate under thrust the Pacific side. We're in the middle where there's no obvious underthrusting of plates of one way or another. And as I said, we recorded from, I'll show you the Honshu earthquake, we recorded along this line, just showing you only one line, P waves from that, and this is the relative arrival time corrected for distance. And you see that these are the seismograms. You see the first arriving P wave is this black in here, making this shape across this region. So what this is a reference, this doesn't tell you very much. When one has to put that into a reference. But what's shown up here, again, these times are now converted. The scale has changed. Notice this goes from 0 to 1.6 seconds. This is 0 to 3 seconds. So these symbols are showing you these arrival times. And this black line is showing what one would predict if the mantle were homogeneous. No variation in mantle structure, just variation in crustal structure. And so one predicts an early arrival way over on the west coast in here because the crust is thin, the crust becomes thicker. One predicts later arrivals, and then because of where these are coming in, again, these are still late on the east side going through thick crust. And these are advanced. So there must be high-speed material somewhere underneath this region to give you this advance. Well, one can imagine three simple possibilities. Underthrusting of mantle lithosphere, this would be the Pacific Plate underneath the west coast, and that is what happens under the North Island. All of these intermediate depth earthquakes occur in Pacific Plate that is underthrust beneath the North Island and beneath the northern end of the South Island. One could imagine eastward subduction of the Australian Plate, and that's what occurs down here underneath the southern end of the South Island in here. There's no question the Australian Plate, oceanic lithosphere, is underthrusting eastward, northeastward underneath this region. Or one could imagine homogeneous thickening of the region. You just thicken a blob up here so that the mantle lithosphere is deeper in this area and the high-speed core lies in the center in here. And we can test these by just trying to fit travel times. So the top, these two are examples of underthrust high-speed material. What are shown are rays traced through a high-speed zone, where here the speed has been increased. This is 0.4 of a kilometer per second and increased to a higher speed in here. This is dipping more steeply. This is high speed, so the rays are bent away from this. And these are the travel times. These are the observations. And again, this is the calculated value. This is clearly a poor fit. This doesn't do very well. This is a better fit, but still these are a little bit late. One can underthrust other direction. Imagine happening under the southern end of the South Island, a steep zone of high-speed material. Again, higher speed by, I think actually these are percent, and that's not 0.4, that's 8.4. I'm wrong, that's speed, 8.4 kilometers per second in here. So this is higher speed, and again, here are your rays, and this is still not fitting that well. You're still late, and the reason is that the high-speed zone is casting its shadow too far to the east. But if we have something that's more similar, more symmetrical, one can get a much better fit to the data, much more like this picture. And in fact, if we just put in a region of homogeneous high speed, dipping vertically, speeds decreasing out, going 8.1 in the surroundings, 8.2, 8.4 in here, 8.5 kilometers per second in here. Again, rays are refracted away. We fit the data quite well. That's for the Honshu, and there were other earthquakes used to draw this conclusion. So I showed you only one profile, but we can reject underthrusting to the west. We can reject underthrusting to the east, but we can accept homogeneous thickening under the middle of the island, as you have here. Just homogeneous thickening. This is faster in this region because the lithosphere has been thickened and the bottom of the lithosphere has been pushed further south. The top, the cold part, has been pushed further south because of the strain. When you shorten in here, you thicken, but material here, before you thicken, would have lain at a shallower depth and moved down, and hence it's higher speed than what's next to it. It's a higher speed region compared to what's next to it. And a summary, the P wave delays across the Southern Alps suggest homogeneous thickening of lithosphere, not subduction of one plate beneath another. Again, continuous deformation of the lithosphere, not underthrusting of one plate beneath another. And one last argument comes from depths of subcrustal earthquakes. This is a profile shown up here, where Northwest is on the left, and there are earthquakes down at 60, 70 kilometers depth. The crust, the maximum depth of the crust is about 40 kilometers under the middle of the island over in here, and you have earthquakes clearly in the mantle. Another profile shown over here, again the same, earthquakes going down to 60, 70 kilometers depth in the mantle, definitely. And this profile is along the island in here. So the Puisaguirre subduction zone is the subduction zone down here. Many, many earthquakes, underthrusting oceanic lithosphere. The Hikurangi subduction zone is the region up in here. Again, many, many intermediate depth earthquakes because oceanic lithosphere is subducted. But in this central part of the South Island, and I should say not just over on the western edge, but in the middle, you have earthquakes going down 60, 70 kilometers depth in the mantle. We commonly believe that earthquakes at this depth in the mantle occur only where the temperature is less than 600 to 700 degrees Celsius. So once again, this is calling for cold material underneath the central part of the South Island, and not subducted cold material, but material that's just advected down because of crustal thickening and vertical stretching of the material. So to summarize, first, the GPS velocities require a width of deformation that's of order 150 kilometers, not 500, but 150. It's not a narrow zone. Shear wave splitting and PN travel times imply large anisotropy, 5 to 10%. This is very large. Ultimately, you cannot, anisotropy can never go infinitely because eventually you can't align the olivine any better than having it perfectly aligned. So this is approaching the maximum possible anisotropy. The polarizations of the fastest quasi-S waves and the orientations of the fastest P wave propagation are parallel to relative plate motion. This requires simple shear, of course, with dynamic recrystallization. This is required to account for the anisotropy, and this dynamic recrystallization occurs at very low temperature. This is quite a surprise. Thickening of mantle lithosphere, not subduction of oceanic lithosphere, occurs beneath the central Southern Alps. Central part, not the southern or northern part, but the central part where one simply has thickened crust and thickened mantle lithosphere. The deformation of relatively cold mantle lithosphere, therefore, is continuous. It doesn't occur by faulting. It occurs by continuous pervasive deformation. And the occurrence of subcrustal earthquakes also suggests temperatures less than 600 to 700 degrees in a very cold environment. And I'm amazed. I hope I didn't talk too fast, Hector, because I finished a little bit early. I thought I had too much to say, as I said, I hope I wasn't too fast. But I have said everything that I want to say. I think that's my last slide. Yes, that's my last slide. So I turn it over to you.
Okay, thank you very much. Let me check if there are some questions. No, there are no questions so far, but I would like to ask you, with respect to the number one of the conclusions about the GPS velocities. So I would like to ask, in that conditions, what will be the best distance of separation of GPS instruments in order to try to get the more sensitive situation for this kind of studies?
Oh boy. Oh, that's as you would know well, we always want more stations. The question you probably are asking is, what's the minimum that you would need? And
Yes.
I suppose you could get by with spacings of even 20 kilometers. So so 1 degree, as you know, that 1 degree is 110 kilometers, or there's a scale, 100 kilometers. Yeah. So this is many more than you need, but you would certainly want several. You'd want probably across here, at least every 20 kilometers, every 10 kilometers may be better. You wouldn't need quite so many down in here. Looking at a plot like this, of course, this is, I should say, this plot is from 2016, and this plot 2002. So this could be refined a lot. This picture is more refined than this picture. But if you want to really see whether there's strain when you get out to this kind of a distance, I think you need a long time to make the errors small. But I would think you'd want at least 10 kilometers for this. But remember, this is a fast rate. The scale here is going from not quite zero, you have to go offshore to get to zero, out to 35 millimeters a year. 35 millimeters a year is the nominal rate across the entire region. And this profile does not include any of these data, I might point out. So this is fast compared to, for instance, what you have in the Eastern Cordillera. In the Eastern Cordillera, you'd definitely want 10 kilometer spacing, I think, but also many years of data.
Yeah, that's right. I am trying is to compare with the Colombian case, thinking about what are the best distance, because sometimes, well, we have the network, but I am very sure that that network is not enough right now in order to understand all the geodynamics and this part of the northwestern corner of South America, and especially on the Pacific coast, that we need more stations. But we have some special conditions that don't permit to us to install some stations there. But in order to make some comparison, that's why my question, I understand that the velocity rates there are larger than ours. But okay, it's interesting to compare.
Yes.
Thank you, Peter.
I agree.
Okay, the other thing, I understand that there are some people trying to use the GPS data for anisotropic studies to compare with some anisotropic studies, but I understand that it's necessary to express the GPS data with the respect to the hotspot reference frame. So,
well,
why is it necessary to do that? Because when you are trying to express the data, we are expressing the data with the global reference frame like an TRF, or sometimes with respect to the Caribbean, or sometimes with respect to South American plate. But it's not easy to understand why it is necessary to do with respect to the hotspot reference frame.
Well, I would disagree about that argument, because if you're comparing with anisotropy is due to strain. It's not due to displacement, but it's due to strain, and finite strain. You have to have enough strain to orient the crystals. And so as soon as you deal with strain, then the reference frame doesn't become important, or it's not very important, because the strain field is, well, you can define the strain field in all kinds of reference frames, but that strain field will be the same unless you're rotating in some strange way. So if you reduce it to strain, I don't think it matters whether you go into a hotspot reference frame or South America or Caribbean or even Nazca. The strain will not be very different.
Okay, gotcha. Okay, we will try to do that.
Yeah. No, I urge you very much to consider strain with
Yes.
GPS because I do think that's the important quantity. Obviously, for earthquakes and faults, yeah, you want to have slip rates on faults. But if you're looking over a larger area, then strain becomes a better target.
Yeah, we already have started trying to do some strain rate maps for Colombia.
Yep.
That is the task for 2022.
Yep.
We already started. We need to understand very well the situation, and now our network has a very better coverage. It's not the good enough, but at least in comparison with the 5-7 years ago, where we have more coverage.
Yep. I understand.
Okay, Peter.
Thank
you very much.
Okay. If it's just, I was going to see if I had that photograph that I mentioned, but I don't. I must have taken it out. I have another photograph, but this is installing GPS stations we also tried to measure vertical components of slip in New Zealand, and well, I haven't been involved in this now for more than 10 years, but vertical components are very rapid in New Zealand, but in order to do that, here's our instrument up here. This, of course, is the solar panel, and winter becomes a problem. Okay, I stopped sharing my screen, and I see you.
Okay.
I hope it was clear. I hope the lack of questions doesn't mean that people are bored and they're not that I'm wasting my time. I hope that's not the case.
I don't think so. I enjoy very much your talk. And when you start talking about GPS, so I am very happy.
Yeah.
Okay, Peter. Thank you very much.
Okay, and
I'll see Okay.
Okay. Bye.